Hey there, this is Max Doolin, and this is the first challenge of the digital signature series from the 6th year of the Spokane Cyber Cup. Although the challenge repo has 5 of them, we only used 3 because 2 of them required manual verification, and I didn't want to deal with that. So, what is the digital signature? Glad you asked. A digital signature is a mathematical way of proving that something was sanctioned by somebody. Similar to how you sign a check, but with a signature of saying this is Max Doolin. It's the same thing, but using math. Digital signatures are used all over the place. For instance, like binaries commonly have digital signatures, like Microsoft Word on Windows does. And this is in order to demonstrate that, hey, this is actually trusted. This is indeed the proper Microsoft Word. Otherwise, you could download a malicious version of it, which would then compromise your computer. But because Windows checks for the signature, it goes, oh yeah, this is actually the wrong one because the data and the signature don't match. Cool. So DSA, or digital signature algorithm, is a common, or it used to be common, digital signature algorithm. There are other ones like RS. I think you can digitally sign stuff with RSA. There's elliptic curve digital signatures. I think Algamal might be another one too. I can't remember. But there's a lot of different digital signature algorithms. So, but this one I think is most straightforward to understand. So we're gonna go through it. So let's read through the prompt. The digital signature algorithm is an algorithm. Good job misspelling this, Max. Cell 5. For digitally signing data using math. Given the message in key material below, sign the data. So in this case, we're just signing the information, or we're just signing the message we're given. Typically, when you're given a message, it would actually be a hash of the message, because otherwise you get this very gigantic number and it gets bigger and bigger and the math becomes very difficult to do. But because these are small numbers, I just kept it as a message, and I didn't for this part. So we're given these values. We're given P, Q, G, the secret known as A, B, K of nonce, and message. It says the result should be R, comma S for the signature. For instance, use 100, comma 10 as the flag. Hence, here's a page for how DSA works. K to the negative 1 means multiplicative inverse of K. Cool. So this challenge is literally just plugging in numbers. I think the one trick is, I think this actually should be modular multiplicative inverse of K. That's important. So that is the one trick to this, is knowing the modular multiplicative inverse is. And it's pretty easy to calculate. In Python, you can use the POW function to do that. But you can also find websites. So just like if you type in modular multiplicative inverse, you'll find it online. You can do it there too. I just like using Python. So if we go to this website, it actually gives us an entire explanation of how to do this. Because there's the signature generation, which is what we're going to do here, and the signature verification. For the signature generation, you can see that there's Q, G, K, and all these other things. All we have to do is follow this to the T. Now, I don't have this nice share screen set up, so what we're going to do is instead we're going to look at the solution, but we're just going to look at the algorithm that it's showing us. And then that also has the numbers, so this works out pretty well. So there's 2 values that we need to generate here. The first one is R. The second one is S, and that is what makes up the digital signature. We can see here that we do G to the K mod P, and then that is equal to X, and then X mod Q. So mod is the remainder of the division process. So for instance, 10 mod 3 would be 1, because 9 divided by 3 is 3, and then there's 1 left over. So this R is what we have generated here, and then we want to compute the S now as well. So we start by generating the modular multiplicative inverse, which is going to be K, which is what this K to the negative 1 is, mod Q. and then we do this modular multiplicative inverse times h plus AR. So R is this value up here, and then the A is another value that we are provided, and then mod that by Q, and that's the signature. So let's do it. Hopefully I don't do this wrong for the millionth time. I feel like I've had to record this video several times trying to get it correct. So I'm going to try again. So for R, we need to do G, so 320 to the K power. So K, or the nonce in this case, is that is known as. And then we do mod P, which is 1031, mod Q, which is 103. So in theory, this should be our R value. And then we need to calculate the S. So yeah, I think that is indeed correct. I've done that one correctly. So then for S, we need to take the modular multiplicative inverse of K. So the way you do this in Python is you want to do POW, which is the exponent. We want to take 25 to the negative first. And here's kind of the tricky part of this, is what the reason you need to take the modular multiplicative inverse is because of the modulo that is present here. So the modulo that is present here is going to be this Q. So Q is equal to 103. So that is the value that we want to get. So now this is going to be multiplied by M, which M is 501, plus A, which is 70, and A is multiplied by R, which we already calculated up here. So theory, that is our S value. And I think I forgot to do the modular multiplicative inverse of that. So now, the modulo of that, not the modular multiplicative inverse. So I forgot to put this Q there, and the Q is 103. And I believe that is correct. So we have 95 and we have 10. So the flag and the format it should be in is 95, 10, because this is how the signature is actually used. This is what you'd pass on. So if you'd actually use this, you would actually distribute the signature, and then people could verify the signature using the public key. So now we've learned how DSA works somewhat, we're going to start messing around with some of the values and hack it like the PlayStation 3 was hacked. So thanks for watching. See you in the next video.